Let's go now to the design of the input stage. The input stage is very important for the noise performance. Later on, we will see if we are going to design an amplifier and we do it in the correct way, then the noise performance of the amplifier is completely determined by the input stage. Other stages don't contribute as much, and we can ignore it at the first step. So now we are only designing with one stage, so there's nothing else. There are no other stages, and we have to design an input stage, this single stage, such that the noise performance is okay. You can do it with LT Spice, but then you have to do a lot of iterations. You have to do a lot of trials, and you have no indication of which way to go, unless you have all the formulas exactly in your head. You know exactly what steps you take. But SlideCap is really very useful in this point. It has a different model. It uses the EQV model, and you have to be sure that the EQV model parameters that describe the noise and the FT and the GM are comparable with those of the BC models of LT Spice. And but if so, then we could do this completely in SlideCap. And that's what we are going to do. We are going to design the input stage, the noise performance in SlideCap. And then later, if we have initial values generated in this way, then we can go to a test bench in LT Spice and see if we are having the correct values there as well. So let's go to the noise performance. The noise model that we use is this. We have the B times ID and the D times ID come from the MOSFET. ID is a channel noise. We ignored until now the DC gate current, so there's no, that's also ignored here. We have the antenna, and the antenna capacitance is L, the length, times the specific capacitance per meter. And we have the gain from the electric field to the voltage, which is given by L. So if we have at the input volt per meter and the noise was specified in volt per meter, then we have to multiply it with the length of the antenna to get the volts at the input of the amplifier. So this is the noise model, and we can transfer this D and B times ID completely to the location of the field, because that is specified. That is specified. What specification do we have? Well, given is that the antenna capacitance is about this, the length is 0.80 meter, and required is a spectral density of 25 times 10 to the power minus 18 volts squared per meter squared hertz, and a crossover frequency, corner frequency of the low frequency noise of 100 kilohertz. That is what we want. Is there a way to go, a straightforward way to go? So we want to know IDS, L, and W based on the noise floor and this corner frequency. Let's make the complete equation. Let's just transfer everything to the input. And then you have an equation like this. And here you see a noise floor, 4kT gamma n divided by GML squared times 1 plus this capacitance ratio squared. And you see in the second term, a term that relates to the 1 over F frequency. You could say FL equals 2kF divided by 3 CISS times this capacitance ratio factor times 1 over L squared. So basically, we have a requirement for F low, and we have a requirement for the floor noise, so we can just fill it in the equation and see what we got. Let's first look at the floor noise, at the 1 over F noise. If you look at the 1 over F noise, you see there is in the term 2kF divided by 3 CISS and this next term there, it is a term that is depending on CISS. And there we have a question. Well, let's look at the formula again, and let's try to find a way to find this answer. The simplest way is, of course, to let CISS approach 0. Then you see that this number, the second term, approaches infinity. So from that, you would say that maybe it would decrease with CISS. But If CISS goes to infinity, you have squared CISS divided by CISS as a final term, which means it also goes to infinity. So in between there is a minimum. And this, my dear students, is extremely important that you can read formulas, because this is designing. It is not jumping into your simulator, trying something to optimize if there is no optimum. First, look at the expression, make a model that explicitly tells you what to do. This formula, this this corner frequency has a minimum for CISS equals the antenna capacitance. Exactly at that point. And if you don't know, you can take the derivative, equate it to 0 and find it yourself, solve it yourself. But it is extremely important that we do not use formulas to calculate the number. That you can do in SPICE, that you can do in any numerical machines. We make models and derive equations to tell us how things behave. And that we need variables, and we need to look at the variables and see what happens. And here we see that we can make the best 1 over F noise if we make the input capacitance equal to the antenna capacitance. That is the design conclusion derived from this expression. And then we can fill it in the number, and we also, and then we have 1 plus CISS divided by this antenna capacitance squared becomes 4, and we can see the floor noise and design GM. And that's exactly the way what we are going to do. So you can optimize it. I will show you later and prove this. You can really find the showstopper immediately from these two expressions. But first, what we're going to do is we are going to design CISS equal to the antenna capacitance. Then we have the product of W and L, easily found from the requirement for CISS and of course TOX and the epsilons. Then we have the requirement for floor noise. And from that one, we can say, well, we need a GM. And the requirement for GM is just solving this equation for the floor noise. And you find this equation for GM. You fill in the numbers. That's all constants. And L is there. And the desired spectrum is in there. And you need 58 millisiemens. And if we have CISS and we have GM, we have FT of the transistor, which turns out to be 6.2 gigahertz. And we know that in a process like CMOS 18, there is a fixed relation between the corner frequency of the 1 over F noise and the cutoff frequency. And if you fill in the numbers for this one, you find out that this relation is about 100 micro. So we end up with a corner frequency of 620 kilohertz, and we need its 100. And this is the lowest we can get, because that is what we found from the fact that CISS should be equal to the antenna capacitance. So we have a showstopper. Maybe on the chat, you can tell me what to do. I have a question on the chat. Yes, I changed the antenna spec to, you can use antenna up to 0.5 meter now. And there is an antenna model that can exactly tell you what is then the capacitance. Okay, what can we do here? Go home, go to the beach. Say you are in a company and something happens like this, what you gonna do? Change the topology, I see. What topology? What can I change? What do you mean with this? Go to another stage in the CS stage? Get hold of the systems engineer. Okay. Well, basically, we did the best what we could in this process. That's what we did. This is what we have. changing the topology doesn't, we cannot use a common drain stage or a common gate stage because we know that the noise sources are equal. So because they are non-energetic feedback stages. So that's not going to help us. Talk to the customer, that would be one thing. We can try to use to get another requirement for this noise. We can try to get, that's what I'm giving you in this course, a longer antenna, because that would help, because there's a clear relation between the length of the antenna and the possibility of having a showstopper. So basically, this is the moment that you go to the system engineer and say, it is not feasible, and here is my argument. And that is very important. It is not based on let's say, trying all kind of things. No, it's really based on fundamental models that we have and say, this is not possible with this process and this antenna. We either need KF to be much smaller, which is a low noise, much more lower noise process, or we need to have a longer antenna. That's all.